All right, so next we're going to hear from John Kallaugher, who's going to talk about a quantum advantage for a natural streaming problem.
So we're slightly ahead of schedule. Do you want me to wait until to start, or? Okay. Do I just press the green button to switch those? All right. Oh, so yes, I'm going to tell you about how to find a quantum advantage for a natural streaming problem. And so, as is the custom, I want to start off by just talking a bit about what we mean by streaming problems here. So, streaming algorithms are a class of algorithms for very large data sets that arrive one piece at a time. So by very large, I mean much too large to fit in main memory. And by one piece at a time, I mean you start with some empty version of the data set and you receive a stream of small updates that gradually build up the whole thing. So for some examples, you can imagine that you have like a router with its tiny memory and you're seeing this huge flood of network traffic and you want to calculate some useful statistics of that traffic. Or you can imagine that I give you the friendship graph of some very large social network as a series of events of the form Alice is friends with Bob, Bob is friends with Charlie, and so on and so on. And you want to learn some properties of this very large graph. Now, there's like a lot of things that you could be interested in with these algorithms, but in the theoretical study of them, we're primarily looking at space complexity. So, given some fixed problem, what is the smallest amount of memory that I could use as a function of either the size of my input and maybe some other parameters and still solve this problem with, say, probability 2/3? Now, like a lot of models of computation, this has a very natural quantum analog. So rather than simply maintaining a classical state, I'm going to let you maintain a quantum state. You're still going to see this stream of updates, and for the purposes of this talk, you should assume this is a classical input stream. So it's your computation that is quantum. And every time you see an update, you get to apply some quantum channel to your quantum state based on the update you've seen. And so the question is, what is the smallest number of qubits I can use to solve some given problem? Now, from the start of the study of these problems, it's been known that sometimes, at least, the answer can be exponentially fewer than the number of classical bits you'd need to solve that same problem. But this initial separation, at least, was for what you might call like a contrived problem, in the sense that the problem was created to prove separations rather than being something that was previously studied in classical streaming. Later on, it's been shown that there is a very natural problem, the moment estimation problem, which also admits quantum advantages. But this is an advantage in terms of how much space you can save when you have many, many passes over the input. So what I want to tell you about is an example of a problem that has been extensively studied in classical streaming and that admits a quantum advantage even in the traditional model where you only get a single pass over the input. And before I tell you what this problem is, I want to start by just thinking at an extremely high level, what is it that we're looking for here? Well, if you want to prove a quantum advantage for a streaming problem, you're going to need two things, right? First, you're going to need a problem that is hard, classically. And you're going to need that proof of classical hardness to be one that doesn't translate to the quantum setting. And if you have such a thing, then you can go ahead and look for a quantum algorithm that beats that lower bound. And as that happens, we actually already have something that satisfies the first of these two bullet points. So the this is the problem of counting triangles in graph streams. This problem, as it turns out, has a lower bound that is derived from a reduction from the Boolean hidden matching problem in one-way communication complexity. Now, I'm not going to talk about the Boolean hidden matching problem or how this reduction works here, but what you need to know for the purposes of this talk is that this is a problem that essentially exists for the purpose of being exponentially harder in classical communication than in quantum communication. And so these lower bounds do not apply to any algorithm that is allowed to maintain quantum state. So the remainder of the talk is going to be me telling you about how you can get a quantum algorithm that beats that classical lower bound for this problem. But before I start talking about the algorithm, I should first tell you what this triangle counting problem actually is. So this is a graph streaming problem, by which I mean you've got this really large graph, and I'm going to give it to you as a sequence of edges in some arbitrary order. Now, your goal, as you process this stream, is going to be to estimate the number of triangles in it, that is to say, the number of 3 cliques in the graph. Now, it might not be surprising to learn that this problem is essentially, intractable. Remember that you're trying to use as little space as possible. This problem is essentially intractable if you're just distinguishing between 0 and 1 triangles. And as it happens, even if I guarantee that there are like a linear number of triangles in the input, you still actually need some additional parameterization to have any possibility of a sublinear algorithm. And the proofs for this actually do apply to the quantum setting as well. So for the purposes of this talk, we're going to assume the following parameterization. We have like a graph with omega of m edges, omega of m triangles, and those triangles are edge disjoint. And so you can also note that I've said omega of m edges rather than m edges, just because it's going to be useful to have m be only an approximate description of the size of the graph. At the very end of the talk, I'll briefly mention what it looks like when we generalize these 3 parameters. So this is the triangle counting problem. We want to get a quantum algorithm that's going to beat the classical lower bound for this. So a natural place to start looking is this instance that we know is hard classically, this one that you get by reducing from the Boolean hidden matching problem, and start out and see if we can beat the classical lower bound there. So this hard instance looks like the following. Remember, you're getting your graph as a stream. So first, you're going to get an m star. And then, in the remainder of the stream, you're going to get a matching and the edges of that matching are potentially going to complete triangles with like the spoke vertices of that star. And so your goal is to figure out, do these eventually complete T triangles, or do they complete 0 triangles? And remember, we're assuming T is linear in M. Now, classically, for some intuition of how hard this should be classically, you can imagine that you're just trying to keep some subset of the edges of that original star. Now, that star you can't really distinguish between the edges of that star, so this basically means you're just going to keep k edges from it at random. And then for every triangle, if there are any triangles in the final graph, for every one of them, you'll have like a k over m all squared chance of getting that triangle. So if t is linear in m, this means you're going to need k to be about root m if you want to have any hope if you want to have a constant chance of distinguishing between 0 and t triangles. And what the reduction from Boolean hidden matching tells you is that this is basically tight up to log factors. So this is the hard classical setting that we want to try and beat. We want to start by trying to beat with our quantum algorithm. And we're actually going to start with something even easier, which is that we're going to forget even about the streaming part to start with, and imagine that we're just dealing with a communication game. So now we're giving Alice that star, we're giving Bob that that matching, and we're asking, can we figure out a short quantum message that Alice can send to Bob that he can then use to determine whether they're in that like triangle heavy or triangle light instance of the problem? And so the message we're going to have Alice send Bob is going to be pretty simple. It is going to be just, so remember, she has a star. She's going to form a superposition over all of the neighbors of that star, all of her spoke vertices, so to speak. And she's going to send that along to Bob at the cost of log m qubits. And then Bob is going to form a measurement basis that he's going to use to measure it as follows. He's going to take each of his edges, VW, in his matching, and he's going to add a basis element V plus W and V minus W. And then once he's done that for all of the edges in his matching, he'll arbitrarily complete that to some basis of the whole state. And then he'll use that to measure the superposition Alice just sent him. So why is that useful? Well, I'm going to define a random variable x that's just +1 if Bob's measurement returns one of his plus basis elements, -1 if he gets one of his minus basis elements, and 0 otherwise. And I'm going to claim that the expectation of this random variable is proportional to the number of triangles in that final graph. So why is this? Well, let's call that central vertex of Alice's star U. Then for each edge VW in Bob's matching, if UVW is a triangle, then he's going to have a 2 over m chance of getting V plus W when he does that measurement. No chance of getting V minus W because it's going to be orthogonal to that superposition. But conversely, if UVW is not a triangle, then both that plus and the minus result will be equally likely, because either there's just one of V and W is present, so they both arise with probability m over 2, or neither of them are present, in which case they both have 0 probability of arising in the measurement. So we have this expectation 2t over m random variable. It also trivially has constant variance since it's bounded in its value, and so we just have to repeat. They just have to repeat this process m squared over t squared times in parallel to get a good estimator for t. And because each instance of the protocol takes log m qubits, this is an O of log m qubit protocol. Remembering that here we're like considering t equals omega m. So this gives us then, for this very specific communication game, this gives us a quantum advantage because we already had that any classical protocol required at least root m bits. And so what we want to do then is go from this very specific this very specific protocol for a communication game on this classically hard set of graphs to something that works when Alice and Bob have whatever graph, and B, something that we can actually implement in the stream. And so in the remainder of the talk, I'm going to tell you how you can do both of these things. And we'll start with the first one, and going in alphabetical order, I'm going to tell you what happens when we generalize Alice's input. So now, instead of a star, we're saying Alice has a general graph, but Bob still has a matching, and that matching maybe completes certain wedges, that is, two-edged paths in Alice's graph into triangles. So previously, when we had the star, Alice prepared a superposition over the neighborhood of that star vertex. Now, we're going to have her prepare a superposition over the neighborhood of every one of her vertices, which you can see is essentially the same as having her prepare a superposition over all of her edges, except every edge will appear twice in the superposition, once in each possible orientation. So now Bob, he's going to receive the superposition, and he's still going to construct a measurement basis from his matching, but instead of adding 2 basis elements for each edge VW he has, he now adds 2 n basis elements, where n is the number of vertices in the graph, by saying if he has this edge VW, then for every vertex u that can possibly be in the graph, he's going to add uv plus uw and uv minus uw. And this is still going to be an orthonormal basis, and when he does this measurement, he's essentially going to get the same effect he had in the previous case, except for every neighborhood, and so he'll still get an estimator that is proportional to t. So Alice's generalization turned out to go through pretty easily, but generalizing Bob's input is going to give us a little bit more trouble. Because even if we assume that Bob only just about doesn't have a matching, say he has like just 2 edges that happen to share a vertex. Now we're already in trouble because our protocol is asking Bob to add, so if we have these edges uv and vw, our protocol is asking him to add u plus v and v plus w to his measurement basis. And these, of course, aren't orthogonal vectors. So he's not going to be able to perform the measurement that we wanted him to perform. So we're going to have to find some way to get around this problem. So to start with, let's think about what we can do in the case where he only kind of doesn't have a matching. That is, he has a pretty low degree graph. Say the max degree of his graph is d. Then he can subsample his graph with probability theta 1 over d and get something that is at least, epsilon close to being a matching, and then, so he can transform it into a matching just by deleting a few more edges. That will let him construct his valid measurement basis, and it will all be at the cost of a factor of d in the expectation of that estimator that we constructed. Because now, for every one of Bob's edges that completes a triangle with Alice's input, there's only a 1 over d chance that that edge actually appeared in the measurement basis and therefore contributed to the expectation. So they have to repeat d squared as many times as they did before. So if d is small, this is not a problem. But of course, in general, d can be as large as n. So this isn't necessarily a satisfactory solution overall. But so what we're going to have to think about then is how much damage can high degree vertices do to us. Like, say that Bob just ignored all of his vertices that were too high degree. What would happen then? Well, to think about that, I want to wind back Alice's input slightly. So now we're back to having Alice have that original star, but Bob has now a general input. In this case, remembering that all triangles that were formed by their 2 inputs were edge disjoint, and so they're all going to have to come from a 2-path going through Alice's central vertex, that means that every triangle in the final graph will be incident to a different pair of Bob's vertices, and so not that many of them can be incident to any high-degree vertex. So in particular, Bob could afford to just throw away all vertices with degree at least 1 over epsilon and only do epsilon m damage to his estimate of the triangle count. So we're actually not in that much trouble in, when Alice's input looks like classically hard. But in general, it can be the case that Alice can have lots of these wedges all pointing to the same Bob vertices. But for that to happen, it has to be the case that she has all of these edge disjoint wedges, all that touch the same vertex. And it turns out that that is actually exactly the scenario in which it's classically easy for Alice to solve this kind of problem. Because what she can do is do this kind of vertex-based sampling strategy that lets her just sample some number of those wedges at kind of constant sample cost per wedge. So the scenario that we have is that those triangles that are hard to count with the quantum estimator are easy to count with a classical estimator, and vice versa. So we can interpolate between these two estimators, and what we end up getting is like an m to the 2/5 space estimator, rather than the root m that that was the best you could do classically. And so that gives you a quantum advantage for kind of the general version of this communication problem. And then, so the last thing I want to talk about is just at a very high level, how do you actually make this into a streaming algorithm? And so because now you don't have this nice separation of the edges you're seeing into an Alice and Bob input, what we're going to want to do in effect is treat every edge as if it belonged to both Alice and Bob. So for the Alice part of this, we're going to prepare this superposition over all the edges in the graph by starting with a superposition over 2m dummy variables, and then have Alice, and so then our algorithm, every time it sees an edge UV, will swap 2 of those dummy variables for UV and VU. And then for the Bob part of this, Bob is going to, every time we see an edge VW, we can't like save up all of these edges and do our measurement at the end of the stream, because we won't be able to remember which measurement we should do. So instead, every time we see an edge VW, we construct like a plus projector, a minus projector, and a projector onto everything else that we use to perform the part of the Bob measurement that corresponds to that edge. And so the final upshot of this is that we end up with we end up for every triangle in the graph having essentially treated its first 2 edges to arrive in the stream as if they belong to Alice, and its third one as if it belonged to Bob. So as promised, I'm just going to put up, I will not read it out, but I'm going to put up what the space complexity of this algorithm actually looks like when you generalize these parameters of the number of triangles and how many triangles can share an edge and so on. And so when you compare this to the best possible classical algorithm, you get that this is a separation that maximizes m to the 2/5 versus root m, and is a bit smaller for other values of the parameters. And I want to note here that in the regime that maximizes this separation, the best known quantum lower bounds kind of disappear, or at least become like log m. So it's still entirely possible that you could get an exponential advantage for this kind of problem. So that's all I wanted to say about triangle counting. And I just wanted to put up as a final note that if anyone is interested in this kind of thing, we are hiring a new postdoc, so please, talk to me or one of the other Sandia people if you're interested in that kind of thing.
So we have time for a few questions.
Thank you for the inspirational talk. What other problems are you thinking of doing using similar methods?
Yeah, so I don't have any good candidate problems in mind where I'm optimistic about being able to get like a quantum, I'm sure there are other problems where you can get a quantum streaming advantage, but everything I've tried to think about has pointed in the opposite direction of insofar as you can show anything, it seems that problems are as hard classically as they are in quantum. So I guess that's a somewhat disappointing answer, but that's kind of what I have at the moment.
I was actually curious to know what triangle counting is used for.
Okay, yeah, so there's kind of two ways of answering it. There are practical, it is related to quantities of interest. So there's this quantity, for instance, in social networks called the transitivity coefficient, which is what fraction of wedges are close to triangles, which kind of gives you a measure of social connectivity. I know it's been used in some spam detection applications, but On the other hand, one of the main reasons I think it's like interesting in kind of a theoretical setting is less because of its direct applications and more because it's the simplest kind of graph counting problem that requires non-local information. Like if I ask you to count the number of edges, that's basically trivial. If I ask you to count the number of length 2 paths, that basically reduces to L2 estimation. So the hope then is that, understanding what makes triangle counting easy and hard tells you what you need to detect like more complex patterns in graphs in general.
Thanks.
All right, great. So let's thank John and all the other speakers of the session one more time. And before we hand over to the panel, I'd like to give the mic to the organizers of the rump session who would like to say a few words.
Okay, thank you, Stacy. So tomorrow at 7:30, after the chess final at the Hilton, we will have the rump session. If you're not familiar with what a rump session is, it's kind of a relaxed evening with a series of short performances, let's say. They can be serious, they can be scientific, but they can also be not at all scientific and not at all serious. So, you can announce some result briefly, you can advertise a conference, you can sing, display a talent. But make sure you, if you have an idea, send it to us at QIP 2022 rump@gmail.com. I think it's been on the slides. Make sure you do that by Wednesday at noon, so tomorrow at noon. If you need some special arrangements, send us an email sooner so we can figure out whether we can accommodate it. And we look forward to seeing you all there.
A quick announcement, actually let me just make 2 announcements. One is again about the testing. Tomorrow, sorry, I'll make a lot of these, but I want to make sure everyone gets the message. We decided to open it up earlier in case, so it'll be open 7:30 to 10:30 a.m. You need to register using the same form you registered before, right? Please register and please try to do it by 3 p.m. today. And we'll need you to pay for that second test, so they take various forms of payment. So please take that into account when planning your day, okay? 7:30 to 10:30 a.m. and make sure you register ideally by today using the same form. All right, so what's up now? We have a panel. We're going to set that up on stage. It'll take just a couple minutes, but I welcome everyone to come in. Everyone's welcome to attend. We had to register, sign-up form for the panel ahead of time. If you signed up on that form, there'll be boxed lunches for you available outside after the panel. So please, let's enjoy the panel first. If you did not sign up for the panel, you're very, very, very welcome to attend. Just when you leave, we ordered extra boxes, but just please leave it for those who registered first. Okay? So we'll be ready in 2 or 3 minutes here, and there'll be six researchers on stage sharing their experience in academia and industry as students in quantum computing. Do you want to say something? No? Okay. So just a couple minutes set up.